Democracy. Government by the people, of the people, and for the people. It would be ridiculous for such a government to use an electoral system where the majority of citizens may not support a candidate. Right? Well, unfortunately, across the globe, democracies use a voting system which is particularly susceptible to this flaw. In fact, there's a fair chance that you live in a society which uses this flawed electoral system. This system, plurality voting, is one of the most simple, hence its widespread use. Every voter may vote for one candidate, and the candidate with the most votes wins. While it might seem like a reasonable extension of majority-based elections, the devil is in the details, and plurality voting is known for having more prominent flaws than its peers. To illustrate one of plurality voting's most prominent flaws, let's run through a simple example. Imagine a grade school class which has just won a pizza party. The teacher, emboldened by the spirit of democracy, runs a poll to find out what pizza to buy their class. Here, let's split the timeline. In one timeline, the teacher offers the class either pepperoni or veggie pizza. When the students each vote for their favorite topping, 16 vote for pepperoni and 14 for veggie. So on Friday, when the teacher arrives to class with a large pepperoni pizza and a movie, 16 of the students are happy with the food. In the other timeline, however, the teacher adds an additional option, sausage pizza. Now, 8 of our students switch their votes to sausage pizza, leaving pepperoni and veggie with 10 and 12 votes, respectively. Using plurality voting, the teacher arrives on Friday with a veggie pizza in hand, to the delight of 12 students. So, what is the problem? Why does the teacher not just order multiple pizzas? That second question is an issue of economics and districting, which are subjects for another video. As of the first question, though, the issue is this. In the first scenario, 16 of our students, a majority, got the pizza topping they wanted. But in the second scenario, only 12 students got their first choice. In fact, because the students were the same across both timelines, we know that the majority of students would have preferred pepperoni to veggie. This is an example of a spoiler effect, and it is a problem for democracies and classrooms across the globe. When I was first exposed to political science through Spanning Tree's great video on the McEvilley-Schofield chaos theorem, which you should check out after this, my question was this. Sure, election systems have issues, but how bad are they really? How bad can policy get for the population without a bad actor? These are questions impossible to answer through the analysis of history, which is why I decided to simulate democracy. Hi, I'm Tazul. Welcome to the lab. Alright, let's simulate democracy. Taking Carl Sagan's advice about apple pies, all we need to do is to simulate all of the individual actions and thoughts of millions of people, their interactions with each other and their environment, and do that billions of times to get our answer. Right? Well, no. Such a simulation would require more code, compute power, and time than I can even conceive of. And for some reason, I doubt that my 5-year-old ThinkPad laptop can handle it. So, what can we do? How can we get meaningful results if we aren't simulating every tiny detail? Fortunately for my CPU, there is a secret in science and engineering which we can exploit. This secret is the principle of good enough. Unfortunately, or fortunately, depending on your philosophy, the world is much more complex than we could ever hope to completely model with perfect accuracy and precision. Take, for example, the classic high school physics problem of predicting where a cannonball will land given a launch angle and velocity. If you've done this before, you know the drill. You use one equation to calculate when the ball lands, and then use that information to determine where it landed. To do this calculation, though, we ignored a large number of factors that would affect the trajectory, such as air friction, non-uniform gravitation, spin, and so on. These simplifications were made to make the problem solvable. What is interesting is that, for many applications, the results of our simple model are well within tolerance. It may come as a surprise to find out that even among higher levels of science and engineering, similar simplifications are often used to make problems solvable. There's a reason that people joke about physicists imagining a spherical cow in a vacuum. If we make no simplifications, then the most efficient way to simulate something is to just do the experiment and let the universe deal with the computation. In my own field of computer science, it's common practice to compare algorithms not by their precise runtimes, but instead by big O notation, which simplifies runtime characteristics down just to their asymptotic behavior. That being said, how should we simplify democracy so that we can experiment with it? The first thing that we can simplify is the behavior of individuals in our population. We don't really care that Tom ate a breakfast burrito or that Julie rode a bike to work today instead of taking the bus. All we care about is what decision they make in the voting booth. We can also notice that the system is impossible to simulate from the top down. If we already knew how the system functioned as a whole, then we wouldn't need to be doing this simulation in the first place. If you are already familiar with some computational modeling, you may know that we have wandered into the territory of agent-based modeling. In this paradigm, we are interested in collective behaviors, and model them by simulating simplified versions of individual agents which update the state of the simulation. The most famous of these models is Craig Reynolds' Boids. This model uses 3 simple rules to simulate flocking and herding behaviors in animals. This simple algorithm is famous for its use in computer graphics for films such as Batman Returns and The Lion King, but has also been used practically in swarm robotics and simulating crowd responses for emergency evacuations. So, what are the minimum features we need to build our agent-based simulation of democracy? Well, to build any agent-based simulation, we need 3 key ingredients. We need a way to represent our agents, a representation of their environment, and a way for our agents to interact with that environment. In our case, our agents are our voters, the environment is the current policy, and their interaction is voting for new policies. Since we are already well within the domain of political science, we might look to the existing literature for help representing these elements. One helpful approach that political scientists have taken is to quantify policies and voter preferences as points in a multidimensional policy space, which allows us to treat each individual and policy as vectors. Now that we have a way to represent our individuals and our environment, we need a way to figure out which policy each individual will vote for. This is often handled in the literature using a utility function. This function takes in 2 elements, the individual and the policy, and returns a single value, the utility, which tells us how good this policy is for this individual. A convenient formulation of the utility function is actually used in the chaos theorem. This approach is to define our utility as an arbitrary decreasing function of the distance between the individual and the policy. This means that as a policy gets further from our individual's preference, the utility, or how good the policy is for that individual, gets lower, and so the individual is less happy with the policy. Using a utility function actually has 2 benefits for our simulation. Firstly, we can assume that our agents will vote for whichever policy provides them with the greatest utility. Secondly, it provides us with a framework for quantifying how well our democracy is operating, as we can add up the utilities across the population to calculate a measure of how much total good the current policy is providing to the citizens. With these building blocks established, we just need to figure out the implementation details. The first thing that we need to do is to place our individuals around our policy space. There are many different ways to do this, but I chose the simple approach of sampling from a n-dimensional normal distribution. This is not perfect, but is likely to be a reasonable representation. If we think of each dimension in our policy space as being a combination of stances on related issues, the central limit theorem should allow us to treat the space as roughly normally distributed. The next thing that we need to establish is our initial policy for the simulation. To get a baseline measurement of the cumulative utility, I wanted to start at the best policy for our population. In order to find this optimal policy, we need to know what utility function we are using. You might assume that the optimal point will always be at the mean of the population, but this is actually only true under the mean squared error, which penalizes the squared distance between points. This is a loss function commonly used in regression, and actually arises quite naturally from the math if you assume normally distributed errors. If we reframe an election as a type of distributed regression, using the mean squared error actually seems quite natural. As such, I chose to use the mean squared error not just for its conceptual fit, but also due to its simplicity and widespread use. Next, we need a way to create proposals which will compete with our current policy in the elections. There are many different ways to do this, and I experimented with quite a few. But for now, I've settled on a simple solution. We sample proposals from the same distribution as our population, but scaled by the average distance to the voters. I chose this method for a couple of reasons. First, it is relatively simple to implement, as we are already calculating the distance between our voters and the policy. It also models the tendency of extreme policies to foster the creation of other extreme policies in every direction due to reactionary responses, commonly called the pendulum effect. With a list of candidates in hand, we just need to calculate the utilities for each voter, count up the votes, select a new policy, and log the cumulative utility for our analysis. With our simulator all set up, let's design the experiment. There are three types of variables that we need to consider when defining our experiment: independent, dependent, and control. We'll start with our dependent variable, what we want to measure, as it can guide the rest of our experimental design. If we think back to the central question of this video, how bad can policy get without a bad actor, we can pick out our dependent variable. While it is tempting to pull something out of this like the minimum cumulative utility, not only would that measurement be susceptible to outliers, but from the chaos theorem, we already know that it is technically possible to reach an arbitrarily bad policy. Instead, we are interested in the typical outcome. So instead of focusing on the worst case, we want to measure the expected cumulative utility. That is to say, the average long-run performance of our system. To increase the interpretability of this value, I normalized it by the cumulative utility of the optimal policy, giving us a metric I will call inefficiency. Inefficiency is essentially then a measure of the percentage by which the electoral system is expected to underperform an ideal system. To compute the inefficiency, we will run the simulation for 1,000 iterations to let it reach long-run behavior, then collect 1,000 samples of the cumulative utility to average and normalize. This procedure will be repeated 1,000 times to smooth out any randomness introduced by the initialization of the policy space. These are our control variables, and will be fixed across all of our experiments. Finally, we need to define our independent variables, which we will vary between experiments. These are easy to define as they are just the remaining inputs to our simulator: the population size, number of policy dimensions, and the number of competing policies. A quick analysis shows that the simulation time increases linearly with each of these, so we want to avoid fine-grained steps at high values. Fortunately, I found through some tests that the majority of interesting behavior happens at the smaller values anyway, so we'll space out our variables exponentially to balance runtime and resolution. To make sure that we can detect multivariate relationships, we will establish test points in a 3D grid, rather than varying each variable independently. To analyze the data and make sense of the patterns that emerge, I am extending the geometric framework of the chaos theorem to help us make better sense of the results. In this further simplified explanatory framework, we consider the voters to be uniformly distributed around a unit circle. Then, for each voter, we can draw a circle centered on them, which passes through the optimal policy at the center of the unit circle. Because utility decreases with distance, the area inside each circle represents the set of all policies that the individual is willing to vote for. Then, we can calculate the area of the regions with enough overlap to win against the optimal policy, which is roughly proportional to the probability of electing a random suboptimal policy. First, let's look at the relationship between the voting population and the inefficiency. In this plot, we can see that as our voting population increases, our inefficiency decreases sharply before leveling off, and does so regardless of the other variables. So why does this happen? Well, using our framework, we can analyze two scenarios, one with 3 voters and one with 5. Looking at the two diagrams, we can clearly see that the overlapping area is much larger with 3 individuals than with 5. If we then do the algebra to calculate the area, we find that the area is 2.7 times larger with 3 voters than with 5. Taking the algebra a bit further, we can express this area as a function of the population, which can be approximated by an inverse square curve, which aligns nicely with our experimental data. Next, let's look at the relationship between the number of competing policies and the inefficiency. If we think back to the spoiler effect, we should be able to predict the general trend present in this graph. When we pull the graph up, we can see that the inefficiency does in fact increase, but along a logistic curve. We can explain this increase and its logistic nature using our framework again. Let's look at an example with 5 voters. With only one competing policy, to get past, it would need to fit into this very small area. However, if we introduce 2 new policies, we can split the vote. These policies can distract 2 individuals, and now only 2 votes from the remaining 3 individuals are needed to pass a policy. This results in the following much larger area, which is 9 times the size of the original. The logistic nature of the curve can also be explained with our framework. As the number of competing policies becomes large relative to the population, each individual will have a different policy on the ballot which is the closest to them, and will receive their vote. At this point, adding further candidates to the ballot has no effect, and the winner is simply a near-ideal policy for a random individual as decided by the tie-breaking procedure. Finally, let's look at how the dimensions of the policy space impact our inefficiency. This relationship is the most complicated, and was the most surprising to me. While the overall trend is a decrease in the inefficiency, we can see that at lower populations, there is a pronounced hump in the data that changes position in some relationship relative to the number of competing policies. Let's see what about this relationship we can explain using our existing framework. To do this, we will need to bring our framework up a dimension. Because we are increasing the dimension and dealing with volume instead of area, I will need to use our measurements relative to something of an equal dimension. To this end, I have elected to use the unit circle and unit sphere as our frames of reference, as they denote the area within one standard deviation of our policy distribution. Calculating this, we can see that the ratio is over twice as large in 2 dimensions than in 3. Using the formula for the volume of a sphere and spherical cap in n dimensions, we can extend this trend to an arbitrary dimension, which gives us a constantly decreasing function. This, however, does not explain the hump we see in the data. While exploring the volume formulas, however, I noticed a similar hump in the volume of an n-sphere, which changes position with radius. My working theory is that this property, along with the density of the multivariate normal distribution, and the distance being squared in the loss function, work together to cause this effect. As the average inefficiency increases due to our other independent variables, the radius also increases. This amplifies these radial effects, which is why these variables have such a pronounced effect on the shape of this curve. That being said, I haven't actually been able to work out the exact math to confirm this explanation, as I'm not a mathematician. So if you have a better explanation or want to take a crack at this math, I'd love to hear your thoughts in the comments. Because some of the design choices in our simulator, such as the policy proposal mechanism and utility function, were, while justified, somewhat arbitrary, I wanted to run plurality voting against a benchmark with no regulation mechanism. To this end, I designed a terrible election system, which always picks a random new policy, sampled the same way that we choose our candidate policies. In a rare piece of good news and publicity for plurality voting, this intentionally poor electoral system performed hundreds of times worse than plurality voting. This means that, despite its flaws and rough edges, plurality voting was still able to protect its democracy from rampant runaway effects and statistical outliers. We can actually use our analysis framework to show how plurality voting is able to do this. If we move the current policy off the center and shade the overlapping area closer to the center green while shading the other area red, we can see that as the policy becomes less and less optimal, not only does the overlapping area increase, encouraging change, but the percentage of that region which is closer to the optimal policy increases. This shows how, without a bad actor setting agendas, the plurality voting system actually does a decent job of limiting the impacts of the chaos theorem. Great. The simulator provided us with some interesting data that we were able to analyze, learn from, and theorize about. But what does it actually tell us about the real world? Well, let's go through our variables one last time and discuss what they can tell us about our real-world democracies. In the simulation, we saw a strong negative correlation between our population and our inefficiency. This trend followed an inverse square curve, meaning that if it holds true in practice and 40% of the population does not vote, as is unfortunately common in US elections, you can expect the elections to be almost 3 times less efficient. Unfortunately, the voter disenfranchisement that leads to low voter turnout rates is rarely so equitable. In reality, groups who are in power tend to disenfranchise demographics which they believe hold opposing political views. This discards valuable perspectives, making democracy less representative and increasing expected inefficiency even more. This shows us that to help improve the efficiency of our democracies, it is important to vote, encourage others to vote, and to work against voter disenfranchisement. We saw that the number of competing policies was positively correlated with inefficiency. This seems to indicate that plurality voting works best when there are only 2 candidates. This is true, as it takes us from plurality to majority voting, which is the best ranked voting system for 2 candidates, according to May's theorem. One might take this to mean that plurality-based democracies work the most efficiently under a 2-party system. While there is a grain of truth to that, and it may be partly responsible for Duverger's law, there are important differences between having 2 options on the ballot and having a 2-party system. In a 2-party system, political expression is essentially compressed onto an arbitrary axis between the policies of the 2 parties. Not only does this decrease the dimensions of political expression, effectively increasing inefficiency, but the axis may not even pass through or near the optimal policy, making it virtually impossible to reach such an optimum. This misalignment of the axis between parties and the optimal policy may also be responsible for what is called the horseshoe theory. Because of this potential for misalignment and their discouragement of nuanced political expression, 2-party systems are an ineffective and potentially even harmful solution to the inadequacies of plurality voting systems. Because of this, we should not look toward 2-party systems to mitigate the issues of plurality voting, but instead look to other electoral systems. While the relationship we uncovered between political dimensions and inefficiency was complex, the general correlation was negative, especially at higher population values, which is probably more representative of real-world democracies. This tells us that it is important to express and consider nuance in political issues. If we cast our votes and make our political decisions off a small number of policy issues, not only are we effectively voting in a lower dimension, but we may actually be ignoring issues that are important to our well-being. This makes our votes less effective and, as a population, makes our elections more inefficient. Therefore, if we want to decrease the inefficiencies of our democracies, we should make sure to weigh the many political issues at play before making a choice, and encourage others to do the same. Thank you so much for watching to the end of the video. It means a lot to me, and supposedly to the algorithm as well. This is my first video, so if you have any advice or suggestions, I'd love to hear from you in the comments. I already have a pretty long list of extensions that I want to make to this simulation, and things that I want to test using this system, but if you have anything specific in mind that you would like to see, let me know. I hope that you enjoyed, and if you did, like to give me some feedback, and subscribe to see similar content in the future.